What the?
That wasn't good. We broke the window from the shop. It went through all the
It
windows.
went through all the windows. Not. I think the last one is intact. Yeah, the last one is broken, but not all the way through.
Whew.
Wow!
And that's why we have the blast screen.
That is.
Hi everyone, today we will talk about what is the need of analyzing the stresses on the inclined planes, and that too we will derive a small equation for the stresses on the inclined planes whenever there is a force in the unidirectional or when one of the force is acting. So in the previous video you might have seen a cylindrical shaped rod, which is acted upon by a compressive force, a vertically downward force. So here, if you watch the cylinder from the side view, you can actually see a rectangle, right? Even though the force is acting in the vertically downward direction, it was not broken in the horizontal or in the vertical direction, but at certain inclination like this, right? Most probably, most of the times, this inclination will be 45 degrees to the horizontal. So here, so actually, why this actually happens here? Because the stresses on these planes are actually got increased than the maximum permissible limit. So that's the reason why on this plane, there is a shearing force which is acting, which is due to that shearing force, since the maximum it is more than the allowable shearing force, so that's why the material got broken here on this inclined plane, not horizontally or not vertically. So that's why so we will take some three-dimensional basic object and we will try to derive an equation for the stresses normal to this plane and stresses along this plane, so that we can have clear understanding of what is actually happening inside of the body, right? So let me take a cuboid shape, some basic three-dimensional element, 3D box. Okay, this is the 3D box that I've considered. These are the non-visible edges. Okay, the plane that I'm about to consider is this one, which is at an inclination to the vertical at an angle theta. Okay, so usually what do we do if you want to find the stress? Means we used to apply force per area, right? But whereas here the area of this plane is A dash, the area that we generally consider is this one. This is the area that we generally used to consider, during the stress magnitude. So what do we do here now is, first we'll have to calculate the area, this area here, this plane's area. It is actually given by the inclination of this plane with respect to this plane, because even if you assume it as some unit quantity, you can actually find the area of this plane. If this is say something like some a, then this will be a dash will be equal to a by cos theta, because a is like this. If you resolve this one along this vertical plane, then a dash will become a, right? So a dash cos theta will be equal to a, so that's why a dash will be equal to a by cos theta. Clear? I hope it is clear. So let's move on. I'm gonna draw the 2D drawing of this cuboid shape here, whatever that I've considered. So this is the force sigma x. Let us consider a force of sigma x, which is acting. I'm considering a tensile force. Initially we'll talk about the compressive force. If it is a compressive force, means there will be a negative sign. Okay, this is the plane that we are trying to analyze. This is the normal force, and this is the shearing force on this plane. So how to find out for the resolve of this sigma n and tau? Let us resolve them. I'm going to rotate this one like this so that you can understand what am I actually trying to do here. So I am considering this plane here. So let me draw a line along this line, and let me draw another line along this line. If this angle is theta, now this component will become sigma x cos theta, right? So similarly this one will become sin theta, sigma x sin theta. So let's put them in the equation form. So here, opposite to this one, here sigma x is acting in this direction, and sigma x cos theta is acting in this direction, and tau is acting in this direction, and this is direction. Sigma x sin theta is acting in this direction. So if we equate these two, but whereas the forces have to be equated, so we have to take the area as well. This is sigma n, this is sigma n into a dash into a dash and into a. Since we are resolving the forces, so let us place them in the equation form. Sigma normal into a dash will be equal to sigma x into cos theta into a. Since a dash is equal to a by cos theta, sigma x into cos theta into a will get cancelled out. A will get cancelled out. So sigma n is equal to sigma x cos square theta. Now what about this tau? Similarly, these two are in opposite direction. It's like, see, we are assuming that the body is under equilibrium, which means even though there is a force in this direction, or even though there is a force in this direction, this body is in stable equilibrium, which means both the forces are equal only, then only this body will be under static equilibrium, right? So that is what we are doing here. We are assuming that, or if you observe this sketch, on this sketch, if I am applying equal magnitudes of forces in both the directions, what happens? This will remain stationary in this position. That is what we are trying to do here. We are relating these two. Okay, so tau into a dash will be equal to sigma x into sin theta into a. So tau into a by cos theta is equal to sigma x into sin theta into a. A will get cancelled out. Tau will be equal to sigma x into sin theta into cos theta. In some textbooks it is also written as sin 2 theta divided by 2. This is the stress which is responsible actually for the this inclined plane failure. Here on this inclined plane only the stress became maximum because of this shear stress. Because see, sin theta into cos theta is there, right? So sin theta into cos theta, if theta is 0, sin theta is 0 means this entire term will become 0. Or if theta is equal to 90, cos will be 0, right? So that's why it has to be maximum at 45 degrees. So most of the times whenever there is a force, axial force acting on the bodies, so it will always try to fail at this inclination, okay, unless there are no impurities at all, it will fail at 45 degrees most of the times, most of the cases. So that's why we need to analyze the inclined plane so that we can get the inside view, inside idea what is actually happening inside of the body, rather than just taking this area and analyzing this stresses, and we can say that okay, our design is safe, but whereas in the inside on the inclined planes the stresses are different. Okay, these are just give you an idea of what might actually happen inside of the body, and what is actually happening on inside inclined planes. So it will actually eventually result into a finding the maximum and minimum principal stresses and principal strains. So we'll talk about them too, but for right now I'm gonna end this class with this one right now. Thanks for your time.